In this video, we will discuss the basic properties of the gradient and also interpret the gradient in terms of normals to hypersurfaces and directions of greatest increase and all that. So first, some basic properties of directional derivatives are rather obvious. I'm not even going to bother stating them. These are things like dv of f plus gx is equal to dv fx plus dvgx. So such things are very easy and are obvious. I'm going to leave it to you. So let me begin by stating a proposition and not proving it, because this is also a very easy proposition. This involves the gradient. So let f comma g from u to r be differentiable at x in u. Okay, then we have gradient of f plus gx is nothing but gradient of f at x plus gradient of g at x. We also have gradient of cf at x is equal to c times gradient of fx, and finally we have gradient of fg at x is equal to g of x gradient of f of x plus f of x gradient of g of x. These are all straightforward properties to prove, and I'm going to leave them to you to work out the proof. Okay, we also have a chain rule, and this chain rule is somewhat involved, so I'm going to prove the chain rule now. Proposition: let f from I to u be differentiable at x and I. Recall I is an interval in R, and obviously g and g from u to R be differentiable at f of x. Okay, so here I'm going against the standard convention of having f from u to R. Here we have g from u to R. U subset of R is of course open. Then g composed with f is differentiable at x, and g composed with f prime at x is nothing but dg of y, the derivative of the function g at the point y, multiplied by this quantity f prime x. Okay, not multiplied by, I'm sorry about that, acting on the vector f prime at x. Okay, dgy is a linear functional, so it eats up a vector and spits out a scalar. This same expression can be written as gradient of g of y dot product f prime x. So let me bold the dot. Okay, so this is one version of the chain rule. Okay, let's see a proof. So we can of course write, let y be equal to f of x. We can of course write g of f of x plus h minus g of f of x is just dg f of x times k plus e of k, where k is by definition f of x plus h minus f of x. Okay. Now what we are going to do is divide by h on both sides. Okay. So what we will get is g of f of x plus h minus g of f of x by h is equal to dg at f of x by h into acting on k plus k by h, not k by h, sorry, e of k by h, e of k divided by h. Okay. Suppose we could show that e of k by h, by norm h to be more precise, actually norm is not needed because h is just a single variable, it's just a real number. Suppose we could show that e of k by h goes to 0 as h goes to 0, then we are done, because this particular quantity k by h, as h goes to 0 is nothing but f prime at x, right? Because this quantity is nothing but f prime at x, so this whole thing will just become dg f of x acting on f prime of x, and if this goes to 0, then we would be done. Now observe that this function e was coming from the definition of the derivative of g, so e is sublinear. Okay, so e is sublinear with respect to k, remember that. E is sublinear with respect to k. Okay, so now so assume k is not 0 for the time being. You will understand why I'm making this assumption. So we want to do e of k by h. So what you do is you multiply and divide by norm k. So you will get e of k by norm k into norm k by h. Okay, now observe, this is valid because I'm assuming k is not 0. This term goes to 0 as h goes to 0. Why is that the case? Well, because as h goes to 0, k must also go to 0, because recall that k was f of x plus h minus f of x, and f is going to be continuous at x because it's differentiable at x. So k will go to 0 as h goes to 0. So e of k by norm k will go to 0 because e is sublinear. Now this quantity norm k by h will be bounded. Okay, that's because this quantity k f of x plus h minus x by h, that is ultimately going to give you the derivative at x, which we know exists. So this norm h by k will remain bounded in a neighborhood of h equal to 0. So at least when k is not equal to 0 and if h goes to 0 and k is not equal to 0, then this quantity can be made really small. Of course, if k is equal to 0, we already know that e of 0 is just 0, right? E of 0 is just 0. That's just because e is coming from this definition of the derivative of g at x. Always the error function will take the value 0 at 0. Okay, so since e of 0 is going to be 0, this quantity e of k by h is already 0 when k is equal to 0. So irrespective of what happens as h goes to 0, even if k is 0, we get 0. If k is not 0, we can make this quantity really small because this quantity is bounded and this quantity is going to 0. Net upshot is the fact is the fact that limit h going to 0, e of k by h is equal to 0. In other words, we are done. So what happens is, as h goes to 0 here, this expression here goes to dg fx acting on f prime of x, and this quantity goes to 0. So we are done. Okay, so this concludes the proof of the chain rule for the the derivative in for scalar valued functions of a vector variable. Now we are going on to interpreting the gradient. Interpretation of the gradient. So all of you are familiar with this, no doubt, from a basic course on multivariable calculus. You would have definitely learned that you get the gradient measures the direction of maximum increase and so on. Let's make this precise. So let f from u to r be differentiable. Okay, now we know that if v is in Rn, v is not 0, then the directional derivative along v at the point x is nothing but the gradient of f at the point x dot product the vector v. Okay, now we already know that the Cauchy-Schwarz inequality is going to tell you, which applies for more general inner products. So specifically it applies to the dot product. So modulus of this is less than or equal to the norm of the vector f of x times the norm of the vector v. Okay, and in fact we have equality. Recall from our study of normed vector spaces, we have equality if and only if v is a constant multiple of this gradient. Okay, now restrict v to be unit vectors. Okay, once you restrict v to be unit vectors, then it is clear that the maximum possible directional derivative occurs when v is nothing but nabla fx gradient divided by the norm of the gradient. This is going to be a unit vector. I'm assuming the gradient is non-zero, okay, for this to make sense. So in other words, the gradient gives you the direction of the maximum rate of change of the function. Okay, so this is the standard interpretation of the gradient. For that, actually you require the Cauchy-Schwarz inequality to show this. Now another interpretation of the gradient is that it gives you normals. So I'm going to make that precise now. For that, we need a definition of the hypersurface or the level hypersurface of a function. Okay, so we will explore hypersurfaces more when we come to manifolds in a later chapter, but for the time being I'm going to give an ad hoc definition. So definition, this is the definition of a level hypersurface. Okay, so let f from u to r be C1 smooth. What do I mean by C1 smooth? Just means that all partial derivatives exist derivatives exist and are continuous. In particular, f will be differentiable in u because of the theorem that we have established earlier, that if partial derivatives exist and are continuous, then the function is differentiable. Okay, so let f from u to r be a C1 smooth function and assume f of x equal to some c. Okay, so for some x in u. So you're fixing a point x in u, and the value is at the point x is just c. Okay, now furthermore, if assume that if f of y is equal to c, where y is coming from u, then the gradient of f of y, the gradient of f at y, to be more precise, is not 0. Okay, what we are assuming is that for all points in in u, we are calling those points y, all points y in u, such that f of y equal to c, the gradient should not vanish at that point. So we are going to assume that the gradient does not vanish at any point at which f takes the value c. Okay, in this scenario, we define the level hypersurface of f at c to be the set S by definition equal to the pre-image of the point with c. This is just y in u such that f of y equal to c. Okay, so a level hypersurface of a function is just the inverse image of this value c. Okay, a hypersurface in Rn is a set which coincides with some level hypersurface. So it's just a set which is going to be the pre-image of some function that is C1 smooth and such that the gradient does not vanish and so on and so forth. So some level surface of a C1 smooth function. Okay, so this definition might seem a bit complicated, so it's good to see at least one example. We will see many more so in the future when we study manifolds. So let's just see one example to just get an idea of what is going on. Let's just take f of x comma y comma z to be x squared plus y squared plus z squared minus 1. Okay, now note that this gradient of this is 2x, 2y, 2z, and the gradient is not 0 unless x equal to y equal to z equal to 0, right? So take the level hypersurface at c equal to 0. That will give you exactly the unit sphere. That will give you the unit sphere in R3, and this is going to be a level hypersurface because the gradient does not vanish at any point on the unit sphere. Okay, now one remark I'm going to make: the reason why we are assuming that this normal, this gradient, grad f of y is not 0 is because that is going to give you the normal. So a level hypersurface is sort of a figure for which there is a well-defined normal at each point. All this will make more sense when we define manifolds, but for the time being we can make this precise in an ad hoc way. So I'm going to define what the tangent plane to a hypersurface is. So you'll have to bear with me for a few more weeks before we precisely define what a manifold is, and this will make sense. Definition. So let S subset of U be a level hypersurface. Okay, of the C1 smooth function. F from U to R with C equal to 0. Okay, I'm going to of course assume that level hypersurfaces are always non-empty. Okay, I'm going to assume that there is some point that F takes the value 0. We define the tangent plane at X in S denoted by Tx at S to be those vectors V in Rn such that we can find a C1 smooth curve gamma from -1 1 to S such that gamma prime at 0 is equal to V, and of course gamma of 0 is equal to X. Okay, so what is this definition saying? You want to define what the tangent plane at the point X on this level hypersurface is. So what you're doing is you're considering, so let's draw a crude picture of what is happening to get an idea. So we have something like this in space. This is supposed to be our level hypersurface. We are focusing on this point X. And I'm saying that to define the tangent plane at this point X, just consider curves that pass through this point. There could be many curves, but the key fact is these curves, the image of these curves should all lie within the hypersurface. They must not move outside the hypersurface. Okay, now what you do is you look at the various derivatives, that is the tangent vectors of these curves. Okay, put them all together and call them the tangent plane. Okay, now of course the picture I have drawn is again inaccurate, because these vectors that I have drawn here, these vectors, they are all going to be situated at the origin, but I have made a remark when we discussed these vector valued functions of a scalar variable, that is curves, that we will usually translate the vector and make it emanate from the point X. So we are just considering all such vectors that arise this way. Look at all the possible curves passing through X, look at all the possible tangents of these curves at X, put them all together, call them the tangent plane. Now we don't yet have the tools to prove that this tangent plane is a vector subspace of Rn. One reason why we took the vectors gamma prime at 0 and not just X plus gamma prime at 0 is because we want the tangent plane to be a subspace. So 0 should in particular be an element of this tangent plane. We don't have the technology yet to prove that this is going to be a subspace of Rn, what we have defined, but all that will come later. So for the time being, I have done this just to interpret the gradient as the normal to the hypersurface. All this will make more sense once we study manifolds. Okay, so we have done some abstract definitions. At least we must gain something out of it. We gain this proposition. Let S subset of U be a hypersurface. Arising as the level hypersurface level hypersurface of the C1 smooth function, f from U to R at C equals 0. If V is an element of Tx at S, X is of course in S, then gradient of f at X dot product V is 0. So in other words, the gradient is normal to the tangent plane. So proof, this is looks very complicated, but the proof is even shorter than the statement. Let gamma from -1 to 1 to S be a curve, C1 smooth curve of course, C1 smooth curve such that gamma of 0 is equal to X. Okay, then f composed with gamma is identically 0 because f is going to be 0 on S. S is nothing but the level hypersurface of f at 0. Okay, now chain rule tells us that df at gamma of 0, which is just X, acting on gamma prime at 0 is just 0. This is just same as gradient of f of X dot product gamma prime of 0. Okay, so this was a rather easy proof. So the gradient gives you the normal to the level hypersurface, or rather the normal to the tangent plane of the level hypersurface. All this will be made more precise when we study manifolds. This is a course on real analysis, and you have just watched the video on properties of the gradient and interpretation.